Okay, thanks everyone for coming. This is, of course, the first ever U.S. Space Force recruitment session. Just kidding. I do not work for the U.S. Space Force. I actually don't work for NASA either, but I am an aerospace engineer, and that means I solve problems, not problems like what is beauty or what is love, because those would fall within the purview of your conundrum of philosophy. I solve practical problems. Problems like, how do you get a bunch of cargo up to the space station? So I also play a lot of video games, of course. That's why I'm here at MAGFest. And sometimes my career and my hobbies collide, and I play space games. So like here, I've got a screenshot from Elite Dangerous. Pretty cool game. Any Elite fans here? Yeah, got a few. All right. There's one problem with being an aerospace engineer playing space games, though. I notice all of the problems. So in like this screenshot, for instance, we've got a space fighter, and that kind of space fighters. Don't know if they would really be a thing, but they're just so a big. Can't talk. They're everywhere. I'm an engineer, not a wordsmith. So okay, all right. There's a game coming out called Star Citizen. A little bit controversial, but man, does it look pretty. And I can't help but notice here that this spaceship has wings. You may know that there's no air in space. So these are like sim cockpit games. I really like that genre. I also play a little bit of strategy games. This is kind of an old one. Sins of a Solar Empire. Actually, yeah, got some fans of that. Cool. There's an expansion pack for this coming out soon. Like, how many years has it been? 6 years? I don't know. 10 years? Jeez. Yeah. And this is just like, okay, this is fantasy. Like, what the heck are these spaceships? And there's like these things, yeah. It's fun. I still have fun, but today we're not gonna have fun. We're gonna talk about like math. Yeah, math. Math, it's fun. No, this stuff can be fun. You'll see how ridiculous this stuff can get. So, yeah, all these things. TIE Fighter. I think people know this one too. You're flying around in a fighter, getting up real close. Too close for missiles, switching to lasers. Get on their tail, blast. Yeah. This isn't space combat. This is World War I air combat. Because it turns out World War I air combat is a lot more interesting. Well, interesting in the sense of like I'm playing a video game right now and I don't have like a week. So yeah. But sometimes you get video games, or they at least acknowledge the reality of it, and this is one of my favorite moments from a very good video game, Mass Effect 2, that is the reason for the name of this panel.
This recruits is a 20-kilo Ferris slug. Feel the weight! Every 5 seconds, the main gun of an Everest-class dreadnought accelerates 1 to 1.3% of light speed. It impacts with the force of a 38-kiloton bomb. That is 3 times the yield of the city buster dropped on Hiroshima back on Earth. That means Sir Isaac Newton is the deadliest son of a bitch in space. Now, Serviceman Burnside, what is Newton's first law?
Sir, an object in motion stays in motion, sir.
No credit for partial answers, maggot!
Sir, unless acted on by an outside force, sir.
Damn straight! I dare to assume you ignorant jackasses know that space is empty. Once you fire this hunk of metal, it keeps going till it hits something. That can be a ship, or the planet behind that ship. It might go off into deep space and hit somebody else in 10,000 years. If you pull the trigger on this, you are ruining someone's day, somewhere and sometime. That is why you check your damn targets. That is why you wait for the computer to give you a damn firing solution. That is why, Serviceman Chung, we do not eyeball it. This is a weapon of mass destruction! You are not a cowboy shooting from the hip! Sir, yes, sir!
Yeah, so yeah, Mass Effect. For a game with, like, you know, rubber forehead aliens and, like, you know, blue-skinned babes and just all kinds of ridiculous tech and stuff, that's all accurate. And, of course, we could thank Isaac Newton for this. He is pretty deadly in some ways. He's also a bit of an SOB, if you look into the history of Isaac Newton. And for a long time, his theories were physics. And we can learn a lot from them. We still use them, of course. But to a certain order, they're just an approximation. They're an extremely good approximation. But of course, Einstein would come along and tell us what's up. So we'll get a little bit into Einstein later. But for now, let's go with Newton. So you heard in the video, we're talking about Newton's first law. I've paraphrased these from the original because, you know, it was all old-timey speech and it gets a little confusing. So first law, an object in motion remains in motion unless acted upon by an outside force. Now, before Newton, like ancient philosophers would, you get like a ball and roll the ball and it'll stop eventually. And this is how everything works on Earth. It's because we've got gravity holding us down, and then we've got friction. And so, but the philosophers were looking at this and just thinking like, well, the natural state of things must be to remain at rest. And that's not true. Nothing moves unless a force acts on it. And so number 2 gives us our basic formula from which we can build up all of the rest of Newtonian physics. Acceleration is... Okay, thanks, virus scanner. Acceleration is proportional to the force and is in the same direction as the applied force. Simply, this is the equation F equals ma. Force is mass times acceleration. And the third law, this is the equal and opposite law, but I've reworded it a little bit to make it easier to understand. When an object applies a force to a second object, the second object applies a simultaneous and equal force upon the first in the opposite direction. So, you know, the colliding pool balls on a table problem. So combining these laws together, we can do some damage. And we've got our additional law here, Rick Robinson's first law of space combat. If you get an object going to 3 kilometers per second, then on impact, it will deliver as much energy as that object's mass in TNT. And the picture here, this is actually a chip in a window of the International Space Station. This was taken in April 2016, and this kind of thing happens at the space station quite often, actually. This is a 7 millimeter diameter chip gouged out of the window, which doesn't sound too impressive, but this was probably caused by a fleck of paint or a tiny metal fragment no bigger than a few thousandths of a millimeter across. So in space, there's nothing, and you can get going really fast, and nothing's gonna slow you down unless you hit something. And I'll talk a little bit now about orbits, so you get a sense of how this is working. So we've got the Earth. It's a pretty nice Earth, round. And let's say we build a huge tower on this Earth, like say 400 kilometers tall, right? And we're gonna climb up onto that tower, and we're gonna drop a baseball. What do you think's gonna happen to this baseball when we just let go of this baseball? It's gonna fall straight down, because there's still gravity in space. Just going up higher and higher, gravity does reduce in strength, but it's still there. It doesn't. It's not like once you get to space, it just disappears and you're weightless now. But if we throw the baseball, we get this nice arc. And you'll notice that it fell a little bit farther because the Earth is kind of falling away from the baseball as it travels sideways. So you can imagine if we throw this baseball hard enough, it is going to fall towards the Earth and miss. And yes, that's something out of the Hitchhiker's Guide to the Galaxy. That's how you fly. You fall at the Earth and miss. But that's literally how orbits work. Because when the ball falls down over to the left side there, gravity is pulling to the right now, so it's going to go to the right, but it's still falling down. And so you end up getting this orbit just all the way around and around. So it's a little bit early. Let's do something fun. So everyone stand up for a moment. You don't have to, but we're going to get a little exercise. All right. So I'm going to count to 3. Well, I'll count down from 3. 3, 2, 1, go. When I say go, I want everyone to jump. Just jump straight up, pogo. Don't hurt yourself or anyone else. I'm not liable for that. Okay, let's go. 3, 2, 1, jump. Congratulations, everyone. You just experienced weightlessness. I'll have astronaut wings for you on the way out. Just kidding. I have no astronaut wings. However, as soon as your feet left the ground, you were on a ballistic trajectory. Now, I told you to jump straight up for safety, so you didn't go anywhere. But that's exactly the same kind of trajectory you would be on in orbit. And so orbits are free fall. Again, you're falling at the Earth and you're missing. Now, some other things about orbits. Orbits are elliptical. So I'm demonstrating a circular orbit here because it's kind of intuitive, but orbits are all ellipses. A circle is just a special kind of ellipse. And everything in the same orbit goes at the same speed. It doesn't matter how heavy it is or how big the engines are. In fact, if you try to change your speed while you're in an orbit, you change your orbit. And somewhat counterintuitively, if you speed up, then you end up going slower on the other end of the orbit. I don't want to get too into it because we want to get to the weapons. But I just wanted to take a little dig at gravity here. Just a recommendation, in a casual setting, do not talk to an engineer about the movie Gravity. Because it's not terrible. As we're talking about, the video games and movies, they don't have to stick completely to physics in order to, be entertaining or whatever. It's just, there's something about gravity where it's just realistic enough, where it just kind of grates on my sense of engineering and such. And the reason I bring up gravity here is the whole thing where there's this cloud of debris that's going to come by every 90 minutes. It's no, if it's in the same orbit as you, then you're going to be, no, it's not going to come by. Everything's going the same speed. Now, if it were in a different orbit, maybe a highly elliptical orbit, you're in this circular orbit, eventually your orbits could cross paths. But then that's not going to happen every 90 minutes. So speaking of low Earth orbit, so when you're in low Earth orbit, this is a sped up video. This isn't real time, but at 400 kilometers, which is the altitude of the International Space Station, your ground speed is 7.6 kilometers per second, which is pretty fast. So with all that information together, we can finally get to the fun part, which is you don't need weapons per se in order to take someone out. So let's say you're in that low Earth orbit and someone else happens to be in the same orbit going the other direction. So 7.6 kilometers per second times 2. And now let's just drop, I don't know, anything. I don't know, your trash. And then we want to get out of the way because we don't want to become a projectile. and we collide with our enemy spacecraft, or our projectile does. So we can use our kinetic energy equation here. Kinetic energy is half of the mass times the velocity squared. And 7.6 kilometers per second times 2. Now remember that law from earlier. If we go 3 kilometers per second, our mass is, the delivered energy is equal to our mass in TNT. So we're going to divide that by 3. We get 5 approximately. And then we square it. So we're going to deliver 25 of the times the projectile mass in TNT. So you don't really need explosives. And just an aside about explosives, one reason why explosives are so dangerous on Earth is because of the shock wave in the air. So you set off like some C4 or something. Well, one, you're going to get fragmentation, so that's useful in space too. But it's also going to try and push the air out of the way, and you get a shock wave, and then the shock wave can do damage to people or buildings or whatever. So there's no air in space. So instead of relying on conventional explosives, we're probably just going to rely on sheer speed and impact force. So that's one way of doing it. Now, for this, if we're just talking about dropping things out the back of your spaceship, you're going to have to like maneuver into position and then drop your stuff, drop your payload, and then get out of the way. It's probably an option, but it's not always going to be feasible. So if we can come up with a different way of delivering high-velocity projectiles, well, we already got one of those. They're called guns. And I use this picture this is from Firefly. Some of you might recognize it. I use this picture because when they wrote this script, they thought they were being clever. It's like, there's no air in space, and combustion needs air to work. So the gun will need to be in a spacesuit in order to work. It's good thinking. It's not true though. Gunpowder actually has an oxidizer contained in it. That's how it burns fast enough to get the energy to propel a bullet. Which means that guns can actually work in space, and we know this because the Russians did it. So this was something that only really came out after the collapse of the Soviet Union. They actually, this is a render, because we don't have pictures of the actual gun, but the Soviets took an aircraft machine gun, modified it a little bit, and then put it on the space station Salyut 3. And reports vary, but supposedly there was a test fire of this gun. I can only imagine what they were going to use it for. Guns, that's cool. They're a little slow. Remember how we were going like 7 kilometers per second? So some of the biggest guns that we have today aren't even going 1 kilometer per second when they fire projectiles. Now, it helps that our ship itself is going really fast, but we can do better than this. And this is sci-fi too, right? Guns and sci-fi, that's boring. How about rail guns? Yeah, now we're talking. I want to point out a couple of things here. One, of course, so this is a picture of one of the experimental railguns being developed by the Navy. You see how it's in a big warehouse, and there's these big shelves of electronic components in the back? Yeah, these things are pretty complicated. Those are probably banks of capacitors just to try and store the energy needed to then dump into this railgun. So railguns are pretty neat. Getting away from the Newtonian stuff here, getting a little into electromagnetism. So it's a pretty simple mechanism here. When you have current flowing through a wire, it will generate a magnetic field. And so I think I have a laser pointer here, yeah. So can you see that laser? Okay, cool. So we got the current flowing here, and then we're gonna get a magnetic field generated in this direction, following the right-hand rule. And so if we put these two rails next to each other and flow the current as indicated, what happens then, we get current going through this guy here. And following the right-hand rule, when you have current going perpendicular to a magnetic field, it generates a force in this direction. So all you need to do, you have two rails, you have a conductive projectile, and you dump a ton of current through the system here, and that propels the projectile down the rails. And turns out you can get going really, really fast with this. Now, there's one problem with railguns, so you've got current going this way. There's also the magnetic field from the other rail. So if we draw it on each of the rails, it looks like this. And if you're thinking ahead a little bit, you might realize by now you do the cross product and you get forces going this direction. So a railgun is a device which is constantly trying to disassemble itself. And that's one of the big problems with these experimental railguns, is how do we get more than a few shots out of them? But if we do figure that out, 2.5 kilometers per second. That's pretty good improvement. Now I also want to touch on a less studied but still feasible option here. You might have heard them called Gauss guns or coil guns. Either of those is correct. This is kind of a more simple magnetic accelerator. So when you have a coil of wire and you put current through it, it becomes a magnet. Now, a normal electromagnet, you'd put like an iron core in the center of it in order to increase the magnetic field strength. But if you leave the core hollow, it will pull objects through it. So if you can line a bunch of these coils up and then get the timing right, you can pull an object, you like keep pulling an object through the coils, and it becomes a projectile. These haven't been studied as much as railguns. I mean, you can do the math and figure out, we can probably get these going pretty fast. There might be some use for them. A little bit of variety in your electromagnetic guns. The only like practical in air quotes application of this that I really know of is there's a startup that's making these. You can go buy yourself a personal coil gun. And it's got about the same power as like a BB gun, so. All right, so we've gone through here, conventional explosives, not too great. Hypervelocity impactors, yeah, now we're getting somewhere. But now we're gonna talk about relativistic weapons. Yeah, so Einstein's back with a vengeance. So this is our normal kinetic energy equation here. And what Einstein figured out is when things go fast enough relative to each other, your normal physics kind of start breaking down. This is the whole thing about how light is the fastest thing. It's also the same speed no matter how fast you're going. Yeah, I don't want to get into relativity. It kind of bends my brain too. But yeah, the point is, you get fast enough, this doesn't apply anymore. You have to use a relativistic kinetic energy equation. And notice the c in there, that's the speed of light. So it turns out you get an object going fast enough, significant percentages of the speed of light, and you end up dealing impressive damage. So I'm going to run through a few examples here. Our baseline is we're going to accelerate 1 kilogram of mass. Doesn't matter what it is, probably just a metal slug. And just as a little fun physics aside here, this is a rendering of the international prototype kilogram, which until last year was the kilogram. Other measurements are based on natural properties, like a meter is the distance that light travels in a certain amount of time, and time is actually based on how many spins of a certain, I think it's a cesium atom or something. But the kilogram was always just based on, hey, we've got this thing, this is a kilogram. But over time, that mass was changing, and nobody really knows why. So for 2019, they've actually redefined the kilogram as relative to the Planck constant, and being a constant, that doesn't change. So that's pretty cool. So we're going to take our kilogram here, and say we accelerate it to 75% the speed of light. This is massive. This is hugely fast. When it impacts, it will impact with the energy of the Castle Bravo nuclear test, which was carried out at Bikini Atoll. That's 15 megatons of TNT equivalent energy. Yeah, let's go faster. Okay, so at 90%, our energy is going to be about equivalent to the 1980 eruption of Mount St. Helens. So that's 25 megatons. So let's keep going. We get up to 99%. That's going to be about the equivalent energy of the Krakatoa explosion in 1883, or eruption. That's 6 Mount St. Helens explosions. And we've also blown past the largest nuclear device ever tested, which is the Tsar Bomba. This is equivalent to 3 of those bombs, and we're at 150 megatons. And if we get to 99.9% of the speed of light, now, fun thing about relativity, we can never reach the speed of light, but we can just keep putting those 0.9s on the end. We could just keep going and adding energy. And so now we're at 6 Krakatoas, 600 megatons of energy. And if we get to 99.99, just add another 9 on there, we're at 1.5 gigatons, which is equivalent to the entire nuclear arsenal of Earth. Now this sounds pretty awesome. It's like, yeah, we can get incredible nuclear weapon-like power just out of a kilogram. But just to rein it in a little bit, 99.99% the speed of light is a lot of energy. And to accelerate something to that speed, you're going to have to put in actually more energy than what it puts out because of efficiency. Like, nothing is 100% efficient. So if you want to deliver 1.5 gigatons, you're going to have to put in more than that, more energy than the entire nuclear arsenal of the Earth. So maybe not practical, but it's pretty cool to think about. Much more practical are just conventional nuclear weapons. And no matter how you feel about nukes, if you're talking about realistic science fiction combat, there's probably going to be a lot of nukes involved. Now, it seems kind of silly to say this, but in space combat situations, it's probably not going to be as bad as it would be on Earth. You're not going to get fallout. I mean, you're still going to get like horrible deaths, but it's war, right? War sucks. Nukes are pretty interesting, though, because as complicated as the nuclear physics is, the principle is actually kind of simple. So if you get these nuclear compounds concentrated enough, they will go critical, and essentially the atoms just kind of decompose and release a ton of energy, and that's a nuclear explosion. So the first kinds of nuclear devices were this gun style up here. So the little boy bomb, the first nuclear device, was a gun style. And so what we do here is we create 2 pieces. They were using uranium-235. This isotope of uranium, all you have to do is get enough of it in one place and it'll go off. So pretty dangerous stuff. but we cut it in half, so we have half of a critical mass at each end. And then we just use a normal explosives to accelerate one half towards the other. And when the halves meet, now we've got a critical mass, and the weapon detonates. Later, they figured out if we can make a safer nuclear device. I mean, it's nuclear. How can it be really safe, right? But that's what that's what they talk about, is like safe nuclear devices. And so using plutonium instead. Now, if plutonium in its normal state, we get a bunch of it together, it's not going to go critical. But if we could compress it, we can compress it enough to the point where it reaches a critical mass. And the way they did this is with explosive lenses, which is kind of crazy to think about. If you shape the explosive in a certain way, you can guide the explosive wave. And so what they did with the second nuclear device, the Fat Man, is they shaped the charge so that you got this compressing sphere of nuclear, or not nuclear, conventional explosive shockwave, which then impacted the plutonium core and compressed it, causing it to go off. And then later in the Cold War, we reached kind of the ultimate nuclear weapon, the hydrogen bomb. And in this one, you use a regular nuclear bomb just to trigger a second stage. And yeah, pretty brutal, pretty effective. And one thing about in space combat, I'll touch a little bit more on this later, but the ranges are so extreme and you're kind of taking pot shots at each other. This is probably one of the reasons why you'd want to use nukes, is just the amount of energy you have. The devices, they're practical in a way, if you're concerned about efficient warfare. All right. Let's talk a little bit about missiles now. So, if we want, space is big, right? And I was talking about orbits. There's a lot of high energy involved, and getting around is a problem. So, instead of just dropping things out of our spacecraft, you can't just drop a warhead out the back of your spacecraft. You want to get it away, get it towards the enemy. That's the basic principle of a missile. Now, on Earth, we use aircraft, and they have wings. They're based on the principles of lift. And missiles are just pure thrust. Usually, they don't have wings. You just rely on pure thrust energy because they're not going to last very long. In space, everything's kind of a missile. So really, it's pretty simple. Missiles in space are just little spaceships. Now, these are some missiles from various space combat games. The top one there is pretty much just a modern missile. Probably wouldn't need fins on a missile. The bottom ones are a little better. Honestly, missiles, like, mechanically are not super interesting. This is kind of how I imagine a space missile would work, or would look like. It's just a cone. Now, you don't need the cone shape for aerodynamics because there's no air, but having it be heavily sloped is good for defense. You don't want perpendicular surfaces that an enemy could shoot at. All right, I really like lasers. And lasers do not get enough love in modern science fiction, in my opinion. I think they're seen as kind of like retro at this point, because everything was all about lasers in, I guess, the 60s. But lasers are an upcoming technology. They are being used right now. Now, I'll get this out of the way. This picture here, this is another picture from Elite Dangerous. We see these nice, clear laser beams, and you might be familiar that you wouldn't actually see this. You can in certain cases. If there's a medium for the laser light to bounce off of in the air, so you get like a fog machine going, you can see some really nice clear lasers. You've probably seen that at concerts before. Otherwise, the laser light itself is going to be invisible. And for combat purposes, we're probably not going to use a visible wavelength of light. But what the heck is a laser anyway? Well, originally it was an acronym for light amplification by stimulated emission of radiation. And the first lasers were microwave, so they actually called them masers. So that's kind of a cool retro-sounding term for you. But it's a pretty simple principle. What we want is, so light, for instance, the light in this room is many wavelengths, as you're probably familiar with. We want to isolate one wavelength, but more importantly, we want it to be coherent. So instead of kind of coming out and scattering in all directions, we want to get all of our light beams going in one direction, so we can focus it and use it for useful work. And to do this, we need some kind of lasing medium. So ruby is one option, like ruby crystal. And then we're going to put that between two reflective surfaces and then take a source. So we could use a flash lamp, and we light this flash lamp, and we get light, which is going to bounce around inside of this medium. And as the light travels through the medium, the medium is kind of like a sieve, and it's filtering out only the wavelength of light we want and getting it going. So that's how we get the wavelength. To get the direction is the fact that the only way that it can get out is through this mirror surface here. And so at that point, we get a coherent beam of light coming out the end here. And there's all kinds of different mediums. So ruby was one of the original ones, but that's kind of fragile. There's gas lasers, where the medium is actually going to be some kind of gas. And one thing I always notice in science fiction is the lasers are always these pointy things. I kind of wonder if this comes from the maser originally, because maser being microwave, and people who had never seen lasers before, if they're thinking about this, they're like, well, that's like a radio wave, so maybe it'll look like an antenna. So if you think of the old like Buck Rogers type ray guns, where it's got the kind of stacked discs, that kind of reminds me of an old antenna. I don't have any basis for that theory. It's just kind of something I thought of. But lasers being light, your laser weapons are going to look more like cameras. And so these are two real-life lasers. So the left one there was an Air Force experimental airborne laser. I wish I had a picture of the whole vehicle, because they took a 747 and cut the nose off and put this big laser ball turret on the end. And they were doing testing with this for shooting down missiles. Now, as awesome as that sounds, turns out it didn't work too well, because in order to intercept the missile, they would have to be pretty close to it. So, we can't just like fly this thing around North Korea forever waiting for a missile to go off. Now, to the right is a smaller scale laser. This is, not sure the exact application here. It's definitely military. It's probably for shooting down missiles. That's a really big use of lasers, is for something we call point defense. And point defense is something we do today. This is an example of a modern point defense system. This is the Dutch goalkeeper. CIWS stands for Close-in Weapon System, sometimes pronounced CWIS, which sounds really funny to me. But if you know the A-10 Warthog, which has kind of become a meme because of its huge gun, this is the A-10 Warthog's gun, the GAU-8 minigun. So the idea here is There's a big radar dish on top. You detect incoming missiles. Then you fire as many bullets as you can at the missile and pray. So you can imagine with a laser, it's traveling at the speed of light. You probably have a better chance of hitting those missiles coming in. Now, I mentioned wavelengths. So we've got visible light lasers, of course. Infrared lasers are extremely common. That bottom left picture is in infrared night vision. And the soldier there is using an infrared laser for targeting purposes. And what would be really great, though, is if we could get like X-ray or gamma ray lasers. The problem there is generating X-rays and gamma rays. But there is one mechanism that we're really good at for generating those kinds of waves. Yeah. So let's take our laser design here, but instead of just like a lamp, we're going to use a nuclear bomb. This is a real proposal. This is called a nuclear pumped laser, and I think there's a obvious problem with this that you might be thinking of is we're going to blow up our laser. Well, it turns out some smart person did the math and figured out if you design it correctly, you can make the whole device last long enough to get one really powerful shot off. So there's a kind of fun idea in hard science fiction where you kind of combine all of these devices together. You've got a missile with a nuclear pumped laser on the end of it. So you shoot this thing far away from you, and then it points at the enemy and fires a laser blast, which is just like, that sounds awesome. All right, so I'm getting to the near the end of my content here. I just wanted to touch on a couple more things, that possibilities for sci-fi weapons. So how about particle accelerators? These are actually not a bad idea. This is pictures from the Large Hadron Collider. Yeah, you might remember that from when somebody found out that one of the guys who worked there looked like Gordon Freeman, and then they thought that it was going to like end the world or whatever. Yeah. So particle accelerator, kind of like a laser. Not really, though, because instead of shooting photons, which are technically massless, we are shooting actual particles. So there's a good thing there, which is these particles will do more damage. And we can get them going really fast, so we get that benefit of a laser. They have some mass, so we're going to get more energy on target. One problem is the range is going to be reduced by a lot because they will diverge. A laser is really good. Lasers do diverge too, so instead of being a perfect line, it's kind of a cone, but the divergence is very small. With a particle accelerator, the divergence is going to be higher. Still a cool option. Don't see these a lot in sci-fi. One thing we do see a lot in sci-fi are plasma weapons. What the heck is a plasma anyways? It's called the fourth state of matter. So if you get a solid hot enough, it turns into a liquid. You get a liquid hot enough, it gasifies. If you get a gas hot enough, the electrons and all of the atoms of the gas will kind of disassociate, and you get this ionized cloud. It's really hot, really high energy. I got a picture of the sun here because the sun has a lot of plasma in it. And I think like Star Wars weapons have kind of been justified as being plasma-based. There's a lot. It kind of shows up in. I think Fallout has some plasma weapons. It's a cool idea, but it's not really practical because plasma, it's like a gas. If you release it, it just kind of dissipates. And so the question is, how do you keep a plasma together long enough to do anything useful? And we don't know how to do that. There's magnetic confinement methods, but it's like, how do you then fire that plasma. You'd like have to keep it contained. It just doesn't make a lot of sense realistically. All right, so bringing all this together, what does space combat actually look like? It looks a little something like this. Okay, space is really, really big. And these weapons we're talking about, so if you remember, I had the picture of the naval guns. We're already at the point where our regular naval guns can shoot over the horizon. So, and we don't even use naval guns that much. We're using missiles all the time. So we're already at a state right now on Earth where you do not see the enemy you are fighting. And in space, it's going to be even worse than that. So that's obviously why video games go for the whole World War I air combat aesthetic. But real, we can break this down a little bit more. It's not going to just be like nothing and then an explosion. So yeah, things are really far apart, and everything's going to be going really fast. And stuff's probably going to be really deadly. So I was focusing on weapons here, but one reason I didn't focus on defense is because there really aren't many options available. There's armors, and then the video games, we've got energy shields, but we have no idea how to build an energy shield. We don't even know what principles that would operate on. So as far as we can tell, space combat is going to be really deadly, and it's going to be a big game of chicken about who can hit the other one first. But there's still room in here for interesting things. And so if you're thinking about like maybe creating a science fiction universe or something, there's still a lot of things you can do, because this all depends on your assumptions. We're speculating about the future. We don't know what route technology is going to take. Maybe we're going to discover new physics, or there's going to be some game-changing technology. One of the big debates in science fiction is missiles versus lasers. So I talked in there about point defense, and there's a big question of, is the combat going to be clouds of missiles flying at each other, or is that not going to be feasible because our lasers are going to be good enough to shoot those missiles down? And again, that just depends on what assumptions you make about what technology is available. Power is a big one. Power kind of limits everything here. It's your maneuvering capacity, it's your weapons capacity. I didn't talk about it here, but closely tied to power is thermal dissipation, because every time you generate this energy, some of it's going to be waste heat, and you have to get rid of that heat. And that, honestly, that's almost a worse problem than generating the power in the first place. Maneuvering, too. What kind of engines do you have? This is a big problem in science fiction, where they don't think about the implications of their engine system. Because remember, missiles are just little spaceships. So if you've got some super cool, awesome engine, somebody could just slap that on a missile, and now you've got a planet killer, because it can just fly out on into space, keep going faster and faster and faster, loop around, come back, smack into the planet. And there's I don't think this is a binary, but there's definitely tension here between, do you want it to be perfectly hard science fiction, science accuracy, or do you want to just have a fun story? And there's nothing wrong with having a fun story, as much as I might complain about gravity or whatever, that is there to tell a story. However, I don't think these are mutually exclusive. So I've come to the end of my slides. I just want to put a shout out here. There's a website called Atomic Rockets, run by a guy, Winchell Chung. If you remember from the Mass Effect video from the beginning, Serviceman Chung is actually based on this guy, because this website comes up all over the place when people are trying to write realistic science fiction. and it's a great resource, big inspiration to me for my career, and hopefully I've inspired you. Thank you very much for coming. I'm getting told to wrap it up, but I think I've got a few minutes here for questions. So, yeah, thanks everyone. All right, a few rules. Keep it to sci-fi or space combat. Maybe I'll answer some questions about real space stuff too. Try to keep your question brief. I don't want big, long essays. Did anyone see when Elon was at the IAC and his Q&A session? I want to avoid that.
Sorry to cut you short, but apparently the next panel's supposed to start in 10 minutes. There's like no buffer.
Okay, can I get like 5 minutes? Okay, cool. So let's go to you in front.
So, on top of defense, I think there's this idea called Whipple armor.
Oh, Whipple shields. Yeah, so Whipple shields are good, kind of like passive. Okay, so what the idea of a Whipple shield is you've got this really thin layer and it's offset from your hull. So it could just be like something aluminum foil thickness. The important part here is that you have a standoff distance from the actual thing you want to protect. And the principle is the Whipple shield will be destroyed when something hits it. However, if the object coming in is high enough energy, then that object will also kind of be vaporized. And so then you've got that distance, that offset distance, where that vapor can just dissipate. And that spreads out the energy. So that would, from like okay, first of all, real space, we use Whipple shields because we're only worried about space debris. And even though there's a lot of space debris and we're always worried about it, events are still relatively rare. So we can get away with Whipple shields. Now in a sci-fi environment, maybe like civilian vehicles would use Whipple shields. Military vehicles probably wouldn't. There's just better options available. And the big problem with the Whipple shield is once it gets hit once, it's destroyed. So yeah, great question, great reference. Yeah, more questions over there. Oh boy, most accurate? Okay, so, man, hard to choose favorites. Let's see. I read a book recently, Neil Stephenson's Seven Eves. That was pretty cool. Not space combat related, but definitely sci-fi and pretty accurate. Let's see, video games. So there is a really accurate video game. I haven't played it myself, and I've heard conflicting reports on how fun it actually is. It's called Children of a Dead Earth. You know, maybe look up some Let's Plays of it if you're interested. But yeah, very, very cool and detailed video game. Man, when I play space combat games, I'm playing like probably Elite Dangerous because I have a really expensive joystick that I have to justify my purchase for. So, all right, next question. Yeah, you there.
How important is detection of the enemy?
Oh, man. Detection might be more important than weapons. Now, stepping on another landmine here, even bigger than the missiles versus lasers debate is the stealth in space debate. On the one side, you say you can't have stealth in space because space is empty. And infrared detectors would be good enough where you generate any amount of heat and everyone's going to know exactly where you are. And you can't get away with not generating heat. And then there's people who are like, well, there's mechanisms. You could store the heat. You could pump the heat into a laser and get rid of it that way. The reality is probably going to be like, maybe. When that comes to detection, though, so if they're intertwined. Because I guess if you don't believe in stealth in space, then like everyone knows where everything is all the time, and yeah, then it's definitely a game of chicken. Yeah. What's that? Have the Russians tested it? So yeah. I mean, we're always worried. So okay, here's the modern state of space detection. Relatively recently, we had, I forget how large the object was. It was a not insubstantially sized object that passed between the Earth and the Moon, and we did not detect it until it was like almost going past us. And that seems really crazy, considering like the radar capabilities we have now. So there's always room for things to slip by, and so yeah, that's why I take a kind of a more moderate approach to the whole stealth and detection. All right, I think I can take one more. Let's go with you here.
Another question about defensive measures.
All right.
If you've seen sunshine, you know that there are ways to reflect, radiation.
Okay.
Has there been any thought about how to either deflect or prevent the ablation from lasers?
Oh, okay. Laser ablation. There's a few things in here. So one, I haven't actually seen the movie Sunshine. I probably should, because it seems to be kind of a modern classic sci-fi at this point. But if we're talking about like, okay, there's a lot of things here. One, the sun. So if you want to look up the Parker Solar Probe, which is in orbit around the sun right now, they've got a really crazy design there with this massive shield. Now, I think they're using an ablative shield. So if you don't know what ablation is, it's the idea you have a sacrificial layer, essentially. So something really hot's going to come in. It's going to vaporize a layer of your shield, but then the vapor dissipates, and that gets rid of a lot of the energy. So that's a pretty good option. And even in a more advanced sci-fi setting, you might have some kind of ablative shield on like military spacecraft. Another thing here is radiation. So that's charged particles, electrons. Those you could theoretically disperse with a really big magnet. And there's a lot of problems there. You'd probably need some kind of superconducting magnet. The most interesting problem to me is something called quench, which is in a superconducting magnet, if you get the temperature balance wrong, then the whole thing can just explode spontaneously. Okay, I gotta do a little aside here. Sorry, this is like an engineer thing to tell cool stories. But my professor was telling me about a project he saw where they were doing an kind of extreme future interplanetary exploration mission design. And it was like, well, we want to get close to Jupiter, but Jupiter puts off a lot of radiation. So we're gonna make our habitat donut-shaped and put a giant superconducting magnet in the center of it. And so my professor, being a smart guy, was like, but what about quench? That could be really bad. And they said, well, we figured that if the magnet stops working, the whole crew dies anyway, so we don't really need to worry about quench. Explosion or fry by radiation doesn't matter. So I think I touched on that a little bit.
About like reflective properties.
Reflective. Yeah.
Obviously, if you have different wavelengths, different materials.
Yeah, that's true. I mean, I can get into the weeds a little bit. I'm not a laser expert either. The one thing I'll touch on, though, people like lasers, just reflect them with mirrors. It's like, yeah, sort of. If you focus the laser down and you have, say, like, I don't know, a speck of like bug poop on your mirror, that's going to heat up, burn out your mirror, and now it's useless as armor. So, nice idea, but not really practical. All right. They're getting anxious, so I got to get out of here. Thank you very much, everyone, for attending.